Okay, let's unpack this. Imagine for a moment, you're an astronomer, right? You're
Yeah.
staring up at the night sky, instruments tuned to the cosmos, and suddenly you pick up something truly mind-bending, like a powerful, enigmatic signal from space.
Hmm.
What's the very first thing that pops into your head? For most of us, it leaps immediately to, intelligent life, right?
Oh, absolutely. ET calling.
Exactly. Maybe a beacon from some advanced civilization millions of light years away
Yeah.
trying to say hello. But what if that signal, a fast radio burst or FRB, came from somewhere? Well, far more surprising and actually much, much closer to home.
It's a captivating thought, isn't it? That deep-seated human instinct to look outwards, searching for those, like, grand cosmic explanations.
Yeah.
But this specific signal, the one we're taking a deep dive into today, it's truly remarkable precisely because it challenges those initial assumptions in the most fascinating way possible.
How so?
Well, it forces us to reconsider the very nature of what constitutes an astronomical discovery. It's not always something billions of light years away.
Right. So today we're diving into an incredible recent discovery by astronomers in Australia. They detected one of these mysterious, powerful radio bursts, okay? But its origin was just deeply, unexpectedly unusual. We're talking about machinery. Machinery that's been dead and silently drifting in Earth's orbit for over 50 years.
50 years. Wow.
Think about that for a second. A signal that could be mistaken for an intergalactic event, but instead, it's an echo from our own past, like a ghost in orbit.
And what's fascinating here is how it completely flips our perspective, Instead of solely searching the vast, untouched cosmos for answers, this discovery compels us to look right back at our own cosmic backyard.
Right here.
Right here. And it reveals something profound, not just about the universe, but about our own technological footprint within it. It's kind of a testament to how even our abandoned creations can continue to speak to us, in a way.
And that's our mission in this deep dive, to unpack this incredible, almost science fiction-like story. We'll explore what these fast radio bursts usually are, the perplexing nature of their origins.
Which is still a huge topic.
Oh yeah, and how these astronomers meticulously traced this specific signal. And maybe most importantly, what this unique finding tells us about, well, the dangers of space, our ongoing quest to understand the universe, and perhaps even ourselves. It's a journey that starts light years away and ends with a fascinating piece of space junk.
Indeed. It really shows both the astonishing sophistication of our modern instruments and the persistent mysteries that linger, sometimes quite literally, right under our noses in Earth orbit.
So let's start with the big picture then. The cosmic enigma of fast radio bursts, FRBs. These things have baffled astronomers for years, truly standing out as one of astronomy's most peculiar and actively researched puzzles. What exactly are they in, simple terms?
Okay. At their core, fast radio bursts are pretty much what their name suggests. Incredibly brief, yet immensely powerful flashes of radio waves.
Flashes.
Imagine a flash of light, but in the radio spectrum, right? And lasting for only a tiny fraction of a second. They are genuinely one of the most enigmatic phenomena in modern astronomy. We're talking about something that lasts for mere milliseconds, sometimes even nanoseconds. But during that incredibly short duration, the energy output is absolutely staggering.
Staggering.
When they were first discovered back in 2007 by Duncan Lorimer's team using old Parkes telescope data, they were so unexpected and so brief that, honestly, a lot of scientists initially doubted they were real.
Close interference.
Exactly. Maybe terrestrial interference. But then more were found, and their cosmic nature became pretty undeniable.
When you say staggering energy, give us a real sense of the scale here. How much power are we truly talking about packed into such a tiny time frame? Like, what's the comparison?
Okay, try this for perspective. Imagine the total radio energy emitted by 500 million suns.
Whoa, okay. 500 million.
Yep. Now picture all of that energy, that immense cosmic roar, concentrated and squeezed into a time frame of a single millisecond.
A millisecond.
That's the kind of power we're discussing with a typical FRB. It's not just a faint whisper or a distant flicker. It's an astronomical scream that, for that fleeting moment, can momentarily outshine entire galaxies in terms of radio output.
Outshine galaxies.
In radio waves for that millisecond, yeah. This incredible energy density is a key reason why their origins are so hotly debated. We're talking about extreme physics at play here, something really violent.
That's just an astonishing amount of energy from such a brief event. And typically, where do these monstrous bursts come from? Do we have a sense of their usual cosmic address? Are they nearby? Far away?
Traditionally, yeah, FRBs almost always emanate from incredibly deep space.
Deep space.
We've detected them traveling millions, even billions of light years across vast stretches of intergalactic space before their fleeting signals reach our antennas here on Earth.
Billions of light years.
For a long time, the prevailing consensus has been that these are non-technological or natural astrophysical phenomena, not signals from intelligent civilization.
Right, not alien.
Probably not. The sheer distances involved and the immense energy output strongly point to extreme cosmic events. Things like highly magnetized neutron stars, magnetars, or possibly even the mergers of black holes or neutron stars. But the exact mechanisms are still topics of intense research.
Still figuring it out.
Definitely. And some burst only once, while others repeat, which adds, further layers to the mystery. It's complicated.
Okay, so if they usually come from incredibly distant galaxies, millions or billions of light years away, are there any exceptions to this rule? Have we ever found one closer to home, say, within our own Milky Way galaxy? It seems almost contradictory given what you've just described.
That's a crucial question. And yes, there is one known and incredibly significant exception within our own galaxy, the Milky Way.
Just one.
Just one confirmed so far that's definitely an FRB from the Milky Way. That particular source is an erupting magnetar.
Ah, the magnetar connection.
Exactly. A truly exotic type of neutron star with an insanely powerful magnetic field. This one's located about 30,000 light years away.
Okay, 30,000 light years is still pretty far, but it's not billions.
Not even close to billions, no. This Milky Way FRB event, which happened back in April 2020, detected from a magnetar called SGR 1935 plus 2154, was a groundbreaking discovery. It was the first time we directly linked an FRB to a known astrophysical object within our galactic neighborhood.
A smoking gun.
Pretty much, yeah. Before this, their sources were largely speculative. It gave us our first concrete evidence for some FRBs, strongly implicating magnetars in their production. But even then, like you said, 30,000 light years is still a tremendous distance, far beyond Earth's immediate vicinity. It provides vital context to just how vast the distances involved usually are, and how utterly unusual it is to find one close.
Okay, so with that context, colossal power, intergalactic distances,
Yeah.
one maybe closer magnetar exception. Here's where it gets really interesting.
Mm-hmm.
The anomaly detected on June 13th, 2024. Tell us about that specific signal. How did it stand out so dramatically from the typical FRB profile?
Right. So this specific signal was picked up by the Australian Square Kilometre Array Pathfinder, or ASCAP. It's a highly sensitive radio telescope array out in Western Australia.
PACECAP, got it.
ASCAP is designed precisely for these kinds of wide-field surveys and detecting transient events like FRBs. The detection itself was precise, a burst of emission across a fairly broad bandwidth, specifically from 695.5 megahertz to 131.5 megahertz.
That's very specific.
It is. That level of detail in the frequency range is important. It's not just a fuzzy blip, but a clearly defined signal, indicating something quite specific. And what's more, its duration was extraordinarily short, measured in nanoseconds.
Nanoseconds. Even shorter than the usual milliseconds.
Even shorter than many of the deep space FRBs we've observed. Very, very brief.
And the immediate puzzle wasn't just the signal itself, but its calculated location, right? That's where the anomaly truly presented itself.
Exactly, that's the kicker. When astronomer Clancy James and his team at the Curtin University node of the International Center for Radio Astronomy Research started the painstaking work of tracking this nanosecond radio signal, they were immediately puzzled.
Why? What did they find?
The initial localization didn't point to a galaxy millions or billions of light years away, like almost all other FRBs do. Its calculated position was just 4,500 kilometers from Earth.
4,500 kilometers.
Yeah.
That's basically right here. That's barely outside the atmosphere,
Yeah.
relatively speaking.
It's incredibly close, astronomically. This was an immediate red flag, just screaming, not a typical FRB. It was simply too close to be any known astrophysical phenomenon, whether a magnetar 30,000 light years away or something in a distant galaxy.
So 4,500 kilometers, that distance immediately rules out the usual suspects, like those erupting magnetars or distant galaxies.
Yeah.
That must have fundamentally shifted their entire investigative approach, right? Pivoting from cosmic to something much more local.
Precisely. The typical origins are millions or billions of light years away. Even that single Milky Way magnetar exception is 30,000 light years out. Finding something at only 4,500 kilometers from Earth made it unequivocally clear this was not a natural astrophysical phenomenon from deep space.
Had to be something else.
It immediately prompted a search much, much closer to home. The most likely culprit, as their logic quickly led them to conclude, had to be something orbiting Earth. An Earth satellite, or maybe a piece of space junk.
Space junk.
Yeah. This dramatically changed the scope of their search from the entire universe down to just Earth's immediate orbital neighborhood.
And so the scientific detective work began in earnest. They had this precise signal, a location just above Earth, and they had to figure out what could possibly generate it. How did James's team go about tracing this phantom signal from thousands of objects in Earth orbit? It sounds like an astronomical needle in a haystack problem.
It was indeed a classic case of systematic scientific investigation, but, with incredibly precise data. The team leveraged the very specific data points they had, the exact geographical location of the ESCAP telescope that detected the burst,
Okay.
the precise time the burst was received, down to nanoseconds.
Nanoseconds. Oh.
And they combined this with publicly available data on Earth satellites. They use a powerful computational tool, basically, a highly sophisticated celestial GPS called Skyfield, a Python module which lets astronomers calculate the precise positions of celestial objects, and crucially in this case, Earth-orbiting satellites at any given moment in time.
So like a cosmic flight tracker for satellites.
Kind of, yeah. This software takes into account orbital mechanics, gravitational pulls, even tiny things like atmospheric drag to pinpoint objects with astonishing accuracy.
So they were essentially casting a very precise net across all known objects in Earth's orbit. What exactly were they looking for with all this intricate data? Were they looking for something moving in that direction?
Their method involved searching for a very specific coincidence. A match in both time and position on the sky between the detected burst and any known Earth satellites.
Okay, so crossing the line of sight at the exact moment.
Exactly. Imagine overlaying the burst trajectory and timing with the orbital paths of thousands of pieces of space junk, active satellites, even defunct rocket stages. They were looking for that one instance where a cataloged satellite or piece of debris was in precisely the right place at the right time relative to a SCAP's receiving antenna to have generated that signal.
A painstaking process.
Oh, incredibly methodical and absolutely key to understanding how they narrowed down the possibilities from the entire catalog of objects in Earth orbit, which, as you said, numbers in the tens of thousands now.
And what was that moment of revelation? After crunching all those numbers, running all those simulations, checking all those orbital paths, what did they find? Did they get a match?
They did. After painstakingly crunching the numbers and sifting through that vast catalog of Earth-orbiting objects, they found what they described as one viable match.
Just one.
Just one. It was like finding that needle in a cosmic haystack, but with the precision of astronomical data. The match pointed directly to NORAD ID 737.
NORAD ID 737. And NORAD ID 737 is
Relay 2.
Relay 2. That's a surprising identity of our ghost in orbit. And it's not some, cutting-edge secret military satellite, is it? It's something far, far older.
Far from it. This is where the story truly becomes remarkable, almost like a piece of space archaeology.
Right.
Relay 2 is a long decommissioned veteran of space, a silent sentinel from the dawn of the space age. It was originally launched by NASA way back in 1964.
1964, wow.
Yeah. To put that into perspective, that's over 60 years ago now. It was one of NASA's pioneering communication satellites designed to relay television and telephone signals across the Atlantic and Pacific, a vital step in connecting the world back then.
Early days of SATCOMs.
Very early days. But it only remained operational for a very short period, just over 3 years, before being officially decommissioned in 1967.
67.
Yep. So for well over half a century, this satellite has been completely dead, meaning its power systems, its communication instruments, everything is off. Just drifting silently in Earth's orbit, a forgotten relic of the early space age. It has no active components, no power, no way to receive or transmit commands. It's just there.
That's truly astounding. So it's just been up there, silently floating, since, the summer of love. What's its current orbital haunt like? Is it in a crowded area or is it more isolated?
It's been hanging around at a pretty high orbit, as the researchers put it, far above the denser traffic of low Earth orbit where most active satellites in the ISS reside.
Okay, so less risk of collision maybe.
Relatively less, yeah. Its altitude drifts significantly, ranging between approximately 1,867 and 7,648 kilometers. That's roughly 11,160 and 4,752 miles above Earth.
Quite a range.
It is. It paints this picture of a silent, abandoned relic, continuing its slow, inexorable journey around our planet, powered by nothing but the initial inertia from its launch and the subtle tugs of gravity. It's not in a geostationary orbit, meaning it's not fixed over one point on Earth. Instead, it traces out this long elliptical path, essentially a cosmic tombstone moving through the vastness.
And to be absolutely clear, because we've seen this kind of confusion before in astronomy where signals can be tricky, right? This wasn't just sunlight glinting off its metallic surface, making a flash. This was a genuine burst of emitted energy.
That's a critical distinction to make, and the research team was very careful to address it.
Yes, while sometimes confounding signals can arise from sunlight reflecting off space junk, like that infamous case of a defunct rocket stage mistaken for a gamma-ray burst.
Right, I remember that.
The team explicitly clarified that this burst from Relay 2 could not have been the result of reflected sunlight. This was a true burst of emission, meaning the satellite itself generated and emitted the radio waves.
Okay, that's key. It really deepens both the mystery and the scientific significance. It truly adds a new layer to understanding what seemingly dead objects in space are capable of, beyond just reflecting light or radar signals.
So, if it wasn't just reflected light, and it was a genuine burst of emission from a satellite that's been dead for over 50 years, then how on earth did it happen? What are the leading hypotheses for such an improbable event? And which one were the researchers leaning towards?
Well, the researchers were able to narrow it down to two primary possibilities, which they then evaluated for plausibility based on known space physics. Both explanations involve some form of electrical discharge, but the triggers are different. It's a fascinating bit of space forensics, really.
Okay, two possibilities. Let's start with the first one you mentioned, the micrometeoroid impact. What's the concept there? Did a tiny speck of dust really cause something like this? Seems unlikely.
It might seem unlikely, but it's certainly a plausible explanation, and it's a recognized hazard in space. The concept is that an impact by even a tiny piece of space rock, a micrometeoroid, could lead to a plasma discharge. Micrometeoroids are incredibly common in Earth's space environment. They're literally cosmic dust. But even a particle the size of a grain of sand, traveling at orbital velocities of, tens of thousands of kilometers per hour, carries significant kinetic energy.
Right, speed makes a difference.
A huge difference. When such a particle strikes a satellite, it can vaporize the material at the impact site, creating a superheated ionized gas, a plasma. This sudden creation of plasma, or maybe the shock wave from the impact, could theoretically generate a brief radio burst as electrons move and rearrange themselves.
Like a tiny explosion generating radio waves.
Kind of, yeah. So a tiny space pebble could essentially cause a cosmic spark, and this is a recognized phenomenon that could cause such a signal, making it a valid candidate.
Okay, so a mini cosmic collision creating a burst. Plausible. But you mentioned they favored another explanation. And this is where it gets really interesting because it connects to something most of us can relate to on a smaller scale. Electrostatic discharge. Static electricity. How does that work up there, and why is it their leading hypothesis?
Right, this is their favorite explanation, and it's quite elegant, really, even if the scale is cosmic. Satellites, as they travel through Earth's geomagnetic environment, are constantly interacting with the charged particles, electrons, and ions present in space. It's often referred to as space plasma.
Okay.
Think of it like a car driving through a dust storm, picking up static charge.
Gotcha.
Over time, particularly when a satellite passes through different regions of the magnetosphere, or maybe during periods of increased solar activity, it can accumulate an electrical charge. This isn't just on the surface. The entire spacecraft can become charged relative to its surroundings.
Okay, building up charge.
Exactly. And when enough voltage builds up, when the electrical potential difference between parts of the satellite or between the satellite and the surrounding plasma becomes too great, it results in a sudden, rapid release of that stored charge. Boom.
Like a shock.
Precisely. An electrostatic discharge. Essentially a miniature lightning bolt on the satellite's surface, or maybe between its components. And this sudden, violent discharge then generates a burst of radio waves. So yeah, it's like static electricity, but on a cosmic scale, powerful enough to be detected from Earth.
That's a fantastic analogy. Like a static shock, but from a dead satellite that's been drifting for half a century. Is there any precedent for this? Or other observations that sort of corroborate this theory, giving it more weight than the micrometeoroid idea?
Absolutely, and this is what lends significant weight to the electrostatic discharge theory, moving it beyond just, speculation. There was an observational campaign using the Arecibo telescope. The massive radio telescope in Puerto Rico is sadly no longer operational.
Yeah, tragic loss.
Huge loss. Anyway, they conducted research with results published back in 2017. That campaign identified several radio signals centered on a GPS satellite.
An active GPS satellite.
Yes. And what's crucial is that these signals were described as very similar to the burst detected from Relay 2. The Arecibo observations provided strong empirical evidence that electrostatic discharges from satellites can indeed produce transient radio emissions, precisely like the one observed from Relay 2.
So we've seen it before.
We have. It's not just a theoretical concept, it's something we've observed, albeit rarely. And this prior observation provides a direct mechanism for Relay 2's surprising shout. It makes the electrostatic discharge theory very compelling.
So even though the mechanism is understood and has been observed before, the fact that they couldn't identify a specific trigger for this burst from Relay 2 suggests that such discharges are still quite rare from this particular defunct satellite. It wasn't like they could see a solar flare hitting it at that moment or anything.
Precisely. The researchers noted that they were unable to identify a specific trigger for the burst. This implies that while the underlying mechanism of electrostatic discharge is understood, the precise conditions for such a discharge from Relay 2 itself are pretty rare.
Just happened to build up enough charge.
Possibly. It wasn't tied to an obvious solar storm, for instance. This rarity makes the detection even more remarkable. It highlights the extreme sensitivity of ASCAP and, to a degree, the sheer luck involved in catching such a fleeting event from an object that's been silently adrift for decades.
Like catching lightning in a bottle, almost.
Exactly. It truly is a very specific, rare snap from a very old, unpowered piece of equipment. It suggests these discharges happen intermittently, perhaps when the satellite tumbles into a particular orientation relative to Earth's magnetic field, or maybe when internal charge accumulation just reaches some critical threshold after a long period. We don't know for sure what tipped it over the edge this time.
This brings us to the broader implications of this discovery, then. Why does identifying a burst from a dead satellite matter for all of us? I mean, it seems like a very niche astronomical finding, but you're suggesting it actually has profound significance beyond just satisfying scientific curiosity.
It truly does, and on multiple levels. One of the most immediate and growing challenges for astronomers today is the ability to recognize anthropogenic signals.
Human-made signals.
Exactly. Signals that originate from human technology. As our technological prowess in astronomy continues to grow, our telescopes get more sensitive, and at the same time, our presence in Earth's orbit expands exponentially.
With all the satellites, space junk.
Mega constellations like Starlink, yeah. It becomes increasingly crucial to differentiate what's natural and truly cosmic from what's man-made noise. Our instruments are getting so sensitive they pick up pretty much everything.
I can imagine how confusing that could get. Have there been instances in the past where signals from Earth-based tech or stuff in orbit cause confusion, maybe even leading scientists down the wrong path, wasting precious telescope time?
Oh, absolutely. The Relay 2 case is certainly not an isolated incident in terms of confusing signals, and it highlights a persistent challenge. There are well-known historical examples where puzzling signals were initially thought to be something exotic, only to be traced back to mundane terrestrial or orbital sources.
Like what?
For instance, back in the early days of radio astronomy, operators sometimes encountered puzzling signals that were ultimately traced to, believe it or not, a truck driving by a radio telescope.
A truck?
Yeah, ignition interference. Or even a microwave oven being used nearby in the observatory kitchen.
The microwave oven incident. Classic.
It sounds almost comical today, right? But they underscore the challenge of distinguishing subtle cosmic signals from human interference. Even the famous wow signal, that strong, narrow-band radio signal from '77 that's never been repeated.
Still unexplained.
Still unexplained. It highlights this challenge, though in that case, it's still widely considered a candidate for an extraterrestrial signal precisely because it didn't match known human sources. And as we mentioned earlier, there was that case of what was initially considered a putative gamma-ray burst, hinting at a powerful cosmic explosion, but which, after careful investigation, ended up being traced to nothing more than sunlight glancing off a defunct rocket stage.
So Relay 2 fits right in.
Exactly. The Relay 2 burst fits squarely into this category of a surprising, human-made signal that could easily be mistaken for something else if you weren't careful, especially given its FRB-like characteristics.
So the Relay 2 burst isn't just an interesting anecdote. It provides a vital new entry in our cosmic noise cancellation library, you could say. helping us filter out human echoes so we can hear the universe's true voice. It's a critical calibration point.
Exactly. You put that perfectly. It provides an incredibly valuable data point. This finding will directly help astronomers in the future identify the provenance or origin of similar signals. By understanding the unique characteristics of these human-made bursts, whether from terrestrial sources or orbital junk like Relay 2, we can prevent future misinterpretations.
Save time and effort.
Definitely. It allows us to refine our observational protocols, calibrate our expectations, fine-tune our search algorithms, making us more efficient and accurate in our quest to understand the truly cosmic phenomena out there. It's about cleaning up our observational noise so the universe's true signals can shine through unhindered.
Beyond just avoiding confusion for astronomers, this finding also has very practical implications for understanding and mitigating space hazards, doesn't it? Electrostatic discharge sounds like something that could really damage active, expensive satellites.
It most certainly does. The phenomenon of electrostatic discharge, which, remember, is the favorite explanation for the Relay 2 burst, poses a very serious threat to spacecraft.
How serious?
When these discharges occur, the sudden flow of current can damage sensitive electronics, corrupt data, disrupt operational systems, or in worst-case scenarios, even completely disable a satellite. This isn't just a theoretical problem, it's a known hazard that satellite operators actively try to mitigate with special shielding and grounding techniques.
So actual satellites have been damaged by this?
Oh, yes. We've had instances where expensive, vital satellites have experienced anomalies or failures directly attributed to ESD events. The Relay 2 event offers new, real-world insights into this specific hazard, coming from a very unexpected source: a long-dead satellite acting as a silent, unwitting teacher about orbital environmental effects. It's like a direct, passive measurement of how even ancient spacecraft interact with the space environment over long timescales.
So by observing these rare natural discharges from old technology, we can actually learn how to better protect our increasingly valuable assets in space. It sounds like it opens up new avenues for monitoring this threat.
Precisely. This observation opens new possibilities for the remote sensing of electrostatic discharge. What this suggests is that we might be able to develop new ways to detect and monitor these dangerous events from Earth, or maybe even from other satellites in orbit before they cause catastrophic damage.
Like an early warning system.
Potentially, yeah. Imagine a network of sensors or a dedicated telescope array designed to pick up these static shocks from satellites. This knowledge can directly help us design more resilient spacecraft, equipping them with better shielding, more robust electronics, or advanced discharge prevention mechanisms. Ultimately, this leads to better protection for our valuable assets in orbit, ensuring the longevity and reliability of critical infrastructure like communication, navigation, and weather satellites, which, we all depend on daily.
Turning a source of confusion into a source of crucial data.
Exactly. That's the beauty of it.
And thinking back to the core mission of astronomy, looking out into the universe, this really helps refine astrophysical observations too, right? Preventing false positives for things that are truly cosmic, saving time and resources.
That's a key overarching takeaway. This deep dive into Relay 2 reveals a new source of false events for observations of astrophysical transients. Imagine the excitement, the dedication, the sheer human and financial resources poured into investigating what you believe is a groundbreaking cosmic event. Maybe a new type of supernova, a previously unknown black hole merging, or a distant FRB indicating some extreme physics.
Getting the whole team geared up.
Exactly, only to discover after weeks or months that it's just an old satellite releasing some static electricity. This research helps prevent such misidentifications. It ensures that when astronomers announce a truly new astrophysical transient, they can do so with greater confidence. It helps separate the genuine signal from the noise. But in this specific case, the noise itself turns out to be a fascinating signal that we absolutely need to understand, given our ever-growing footprint in orbit.
And the researchers aren't stopping there, are they? This discovery isn't just an endpoint, a closed case. It sounds like it's actually a launch pad for future research and even new ways of observing.
Absolutely. The researchers themselves suggest exciting new possibilities, turning what was once a confounding signal into a new scientific opportunity. They propose things like retrofitting existing experiments, searching for fast radio bursts or high-energy particles, or even developing new dedicated instruments, specifically designed to look for these types of electrostatic discharges from satellites.
So actively look for these satellite zaps.
Yeah. Instead of just being a confusing signal to filter out, these bursts could become a tool for monitoring the health and environment of our orbital assets and understanding space weather effects in real time. It transforms a problem into a resource for understanding our orbital environment and the physics happening within it. We might even learn more about the long-term degradation of materials in space from these observations. Who knows?
Fascinating. And for those who might be wondering about the scientific validity of this incredible finding, has this research gone through the rigorous scientific peer review process? Is it solid?
Yes, it absolutely has. The research paper detailing this finding has been accepted for publication